Okay, this is web assigned 9A, problem number 10. A proton is projected in the positive x direction into a region of uniform electric field. E is equal to negative 5.9 times 10 to the fifth. IK newtons over coulombs at t equals 0. The proton travels 6.20 centimeters as it comes to rest. Okay, so I'm gonna start off with a force. Free body force diagram. Okay. Proton is projected in the positive x direction. Okay, so it's initially going this way. It's initially going this way. Now it travels 6.2 centimeters as it comes to rest. So we have our little charge, and it's moving this way initially. But if it comes to rest, that means it's slowing down, which automatically means there is a force this way that is counteracting this initial movement. So our acceleration, actually this force of the field, I'm sure there's a better way to put this. I'm going to call it F subfield, is pushing the proton back this way, causing it to slow down. And I'm just going to ignore gravity and normal force because I'm assuming it's not resting on anything, and I'm assuming gravity would be negligible in this case. So it's this net acceleration is this way, as the velocity is this way, and then it says it comes to rest, so our velocity at the end would actually v would equal 0. So and we can automatically answer our direction for part A as being negative x direction. If we're calling this direction x, then that means this arrow slowing it down, acting in the opposite way, would have to be negative x. Now we can actually begin to find numbers here. So we have part A. Determine the speed. Now it's asking for magnitude, so I can ignore signs in this case, since I already found direction as the second part of the problem. So I'm going to use E is equal to force over charge. Now given our E is equal to that, I'm going to plug it in. Again, I'm not going to worry about signs because this is just asking for magnitude, and we already know the direction. This is our E value. Let's go to force over, and Q is charge. We know the charge of a proton is 1.67. Nope, that's the mass of a proton. Charge is 1.602 times 10 to the negative 19 coulombs. An easy way to, I'd say, get to this point is not forget that force is equal to mass times acceleration. So to find this acceleration, once I find the force, I can just divide by mass. And this, you can look at the units. So we got newtons per coulomb, and we know coulombs, so we can get force really quick by just multiplying it, even if you don't know the exact formula. E equals force over charge. So then we get newtons, and then with newtons, we can divide by a mass, and the only known mass we could go off of is this proton to find the acceleration of the proton. So then we get F would be equal to so I'm actually just going to do this real quick. I'm not going to multiply anything out, or simplify, I should say. Times this 1.602 times 10 to the 19th coulombs. And again, this unit will cancel out, so I'm left with force. And I'm going to substitute force for mass times acceleration. I'm going to go a step further by substituting for the mass of a proton, which is 1.6. So that's in the negative 27 kilograms. Okay, now I'll put times A. So then our A would be equal to this whole thing up here. Divided by the mass of our proton. Oops. What's going on? And by the mass of our proton. Plug this in the calculator. Good. Yeah, you get that answer. I can do it real quick again just to check. Yeah. 5.66 times 10 to the 13th. And again, the reason I did not worry about the signs of the charge is because we already knew the direction. We only need magnetic part B. Determine the initial speed of the proton. Here we can use a kinematic, seeing as we know the acceleration of the object and we know its final velocity, which is going to be 0 as it comes to rest. We can use the equation that V final is equal to V initial square plus 2a change in x, and again we know the change in x is 0.062 meters, 6.2 centimeters. So if this is equal to 0, this is equal to less the initial square, which we don't know, plus 2a, what we know the a is the a we just solved for. Times our change in x, which I'm just going to convert right to meters right away. Okay. And our negative v initial squared is equal to, and again, here I might just plug in the sign, just as negative, just so I can cancel out this negative right here, make it look a little bit nicer, which is equal to 5.616. I forgot to do. I guess just put the units in. This is Newton. No. This is meters per second. That's 1.062 meters, and you can see how once I take this root, it'll go from meters squared over second squared to meters per second. Now I can erase the root, or the 2 there, just take the root right from here to get our answer equal 2.65 times 10 to the 6 meters per second. And then determine the time interval over which a proton goes first. Again, we can use another kinematic here, which is so nice. The hardest part of the problem would probably be that first part, just finding the acceleration using F equals ma equals F over q. Because then we can just go right into our kinematics that we've known for the past 2 years. So our VF will be equal to our V initial plus acceleration times time. If our final is 0, then we can bring negative V initial is equal to AT. Now, this velocity, technically, this velocity, not technically, it just does. It has a negative sign because we subtracted it. I'm just going to do a few things in one step here. Of our acceleration, which again would have a negative sign because of its direction in this first part. Which I, for the value, I forgot. 5.66 times 10 to the 13th, I believe. Meters per second, and meters per second will cancel. Right? Yeah. Right? T equals 4.62 times 10 to the negative. So this shows just how fast these things are moving, or how fast these things are coming to a rest. Because it's like a billion, right? It's close to a billionth of a second. 4.62 billionths of a second. It happens probably like a million times by the time I finish the sentence. Okay, so set bar, I guess it's kind of a bad model of it, but like, this is our force diagram. Our initial motion's this way, as we can see by our velocity, arrow, and accelerations that way, causing us to come to a rest, which means the forces are imbalanced in our we have a negative acceleration, which is why there's a negative sign next to our x value as we're moving in the positive x direction and slowing down. To then find the actual acceleration from which we are slowing down at, we just do some pretty basic substitutions into our E equals F over Q, substituting F for M over A and dividing the entirety by that mass to find the acceleration, then using our acceleration in the kinematic to find the initial velocity the proton was sent at, to be able to, using this negative acceleration to slow down to complete stop in the 6.2 centimeters, and then using that information for another kinematic, using our initial velocity and our acceleration, we can find the time it took all of this to happen.